Friday.
Okay.
Thanks everyone for coming to this ICRR seminar. First of all, I just want to acknowledge that we're meeting on Bejigal land. So Bejigal people, of course, have been dealing with flood assessment and risk for time, as long as time has existed. So I'd like to extend my acknowledgement and respect to elders past and present and any Aboriginal people joining us today. Today we have Olivia Martius from the University of Bern. Olivia is a professor of meteorology at the University of Bern, and she co-leads the Mobiliar Lab for climate risk. Full name, climate risk.
Yeah.
Mobiliar Lab for climate risk, which is funded by a Swiss first insurer. And today she's going to talk to us about flood assessment and risk in Switzerland. And I'm really, really happy that Olivia is joining us. She's also around for the rest of the week. So if this brings up questions that you want to talk to her about, please get in touch with her. But for now, I'll hand over to Olivia. Thank you very much.
Thank you very much for the kind introduction. Let me know if I don't well hearable at the back. So if I need to speak up, let me know. Yeah, thank you for the kind introduction. Thank you for the invitation, and thank you all for being here. I need to start with announcing that I'm deviating a bit from the abstract. In the abstract, I promised to also talk about hail impact assessments and hail risk visualizations. When preparing the talk, I realized that I don't have the time for both. But as Tim said, I'm here for the entire week. I have time for meetings, and if you're particularly interested in the hail related aspects, please come and see me, and I'm more than happy to show you the tools that we have developed for hail. So today I'm focusing on flood, and I'm introducing a couple of tools related to flood risk assessment in the current climate, in a future warmer climate. Those tools were all developed for Switzerland because, as Tim mentioned, the funding for this research is coming from a Swiss first insurer. So naturally, the focus is on Switzerland, but some of the ideas and concepts can, of course, be transferred to other areas around the world. And I would also like to acknowledge my co-authors, because these co-authors in particular, Markus Mosimann, Lukas Munz, and Martina Kauzlewicz, they have instrumental in putting this tool together. They did all the coding and data analysis. And I'm now here in presenting their work. So first, I would like to give you a very brief overview of different tools that we have developed. They're all gathered at one website, which you can access either through this QR code or through this link. They all have an English version online, and they're freely available, so you can visit them, study. Yes, of course, study them in more detail later on. I will talk about two of these tools today. I will talk about the flood dynamics tool, which presents a time evolution of severe floods in Switzerland, and the risk sensitivity tool, which is a tool that addresses the question of how flood risk will evolve in a changing climate. So, why did we initially develop these tools? We developed these tools because in Switzerland, but also in Australia, we've experiencing flood events that were beyond anything that had happened before, and that were in their scale almost unimaginable before. And the goal was that with tools that would be able to capture even more extreme events, first responders in particular could use these tools to train and to come up with response strategies. But then, of course, also, it's not just for first responders, it's also insurance companies that need to think about the way such events can still be insurable. And also, of course, politicians that need to think about coordination concepts on higher than regional levels to respond to events like that. So the idea was to for this flood dynamics tool to visualize the unimaginable before it happens. So what the tool does, it visualizes the spatial and temporal evolution of a flood. It visualizes also the impacts, and it's meant as a training tool, as I said, for civil protection agencies and for emergency planning. It also should serve as a basis to start a risk dialogue, as I mentioned, with decision makers, with politicians on the local, but also on a more regional or even canton level. This is the administrative areas in Switzerland that I guess are similar to your states, where all the decision making for flood responses and flood management and flood protection are taken. So what the tool also offers, which is novel, is that it provides dynamic view of it basically provides a view of the time evolution of an event, which is important for first responders. Because in Switzerland, first responders, that's mainly the fire brigades and the police, they basically are often, they're not professionals, but rather they respond, they're volunteers, like your lifeguards. And in case of an event, they come in and respond. And traditionally, the first person who called, they would go to this person's house and empty the basement from the water. But then the next person called, and then eventually they're overwhelmed if a really big event happens. And the idea was that these tools can help to approach these responses in a more strategic way, also to train the response before. The tool is basically modeling the whole chain of events, starting with the precipitation input, then going to model hydrological response, the hydrodynamics of the flooding, and then the impact. And as I said, the primary will be civil protection, and it's meant as a tool to prepare. So very brief, some methodological background, how we set up the tool. So we start with precipitation input. The precipitation input comes from reforecast archives of the CMWF. So we used their seasonal and sub-seasonal forecast to extract very extreme precipitation events together with the temperature information, and then fed this information into a hydrological model, use the Cypher model. Then the output of the hydrological model goes into a flood model, a two-dimensional flood model. Then from the two-dimensional flood model, we obtain information on the water depth of the flooded areas and the extent of the flooded areas. We combine this information with the information on the values at risk. Then we use vulnerability, impact functions, loss functions to assess the effects or the impact of certain flood depth, speed of the flow, and then in the end come up with an estimate of the impact. Just a very brief comment on this selection of the meteorological input. In the end, we selected 9 scenarios. I should say we selected 9 scenarios because, in particular, the 2D hydrodynamic modeling is extremely expensive, takes a lot of time to process, because we need to operate models at extremely high resolution. So there's really in the centimeter range matters for these floods. So very costly. So we chose to work with 9 scenarios that are all extreme scenarios. They're at least 100-year return period events in terms of the precipitation averaged across Switzerland. And as I mentioned before, the approach that we used in the end was this approach that's also called unseen, using reforecast archives. The methodological paper is the Kelder et al. Reference. We could also have used observations and statistical models, but decided in the end that because we needed for the hydrological modeling both temperature and precipitation, that these dependencies between variables are quite challenging to model statistically, so that we found it easier to work with these large reforecast data sets. And this is now a first view of the tool. What you can see here is the precipitation evolution, and the blue lines, the width of the blue lines indicates the damages per river section. So the wider the blue line becomes, the more damages we find, or the more impacts we find along a certain river section. And I'm going to show you in a minute. So we have this national view, and then basically we chose a selection of values at risk. We have buildings, people and workplaces, and roads. And just to show you in a bit more detail, so we have generally all the buildings, and then in addition, highlighted here are schools, hospitals. There's also in the newer version nursing homes. And the idea is again that these are buildings that potentially need to be evacuated. So it's again important for the first responders to know whether schools or hospitals are particularly impacted. And then the last, a last point on the roads. So what the model is doing is it identifies flooded roads based on the water depth. So if the water depth is deeper than 30 centimeters, the road is marked as impassable, even for the fire brigades who have trucks that can run on roads that are slightly flooded, but then there's a certain level where even those trucks no longer can pass the road. And the tool also identifies the diversion traffic. So if a road becomes closed, the tool identifies where people need to divert it to still reach certain areas, which is again important for the fire brigades in case hospital is no longer accessible for them, or even the fire station in some villages in Switzerland are in a flood-prone area. So it can also be that the fire brigades actually can no longer exit their own fire station. So this identifying this road closures is also very important for the first time. And then we've identified these hazard classes, which basically indicate damages to buildings or areas where people and vehicles are at risk, and or areas that can no longer be passed by vehicles. So just to get a quick overview. And now I have a quick demonstration of the tool. So we'll choose one scenario, and this demonstration is the worst case scenario. The tool allows you to select the exposure, so either the buildings or workplaces or nursing homes. And then it will give you a first national view in terms of impact, and basically will give you summary statistics for the catchment. And then what is very important is that the tool shows the time evolution. So you can see in this summary statistic the number of affected buildings as a function of time. And what you can see here is something that's actually quite typical for most areas, is that there is at a certain point, there's a very fast increase in the number of buildings. And this fast increase, this is extremely challenging for the first responders, because this means at some stage they will just be flooded with calls for help, and they need to have a strategy on how to triage these calls and to whom to respond first. So this was extremely important for them to see this, that yes, there will be a point in time in such flood event where all bad things come together at the same time and they need to respond. So this was one of the key insights actually of this tool. And for this time evolution, so not just having a map of the entire flooded areas, but showing which areas are flooded first and which areas are flooded subsequently was very. And then it's possible to zoom in on a specific floodplain, and again you will receive summary statistics, number of houses, number of affected people, and then you can zoom in even further, and then you can see a dynamic display of, here in this case the blue indicates the water depth. So you will see which flooded first and which areas are flooded subsequently. And the same again for the road closures and basically these hazard categories. So again, so this point that I made before, so one of the key findings was this very quick increase in, yes, please.
Can I just quickly ask about that increase in the number of calls? Is that window of time the same or similar for each different scenario of flood that you tested, or does it depend on what kind of flood is happening?
Well, the underlying reason behind this is that these are very extreme floods, and in Switzerland the publicly mandated flood protection is set out for a 1 in 100 year event, with basically some of them even working for a 1 in 300 year event. But this worst case scenario is much worse. So what you basically in essence see here is the flood protection breaking down. Yeah. And then basically the dams or water is going over the dams, and then things just go. So basically when exactly this happens varies from one catchment to another, but it's basically once.
So they need to use the tool to see how long that period of time is going to be. Yeah. Thank you.
Yeah, so these flooded areas expand very quickly and in a short amount of time. A large number of people are. Yeah, and we confirmed that for many catchments, these scenarios that we chose were indeed more extreme than anything that had been seen before. So the methodology is actually detecting or visualizing such unimaginable situations. And now, what are the real-world applications? So some Swiss fire brigades, they have mobile dams, flood dams. As you can see here, they're called beaver dams. And so what we did is we collaborated with one city where the fire brigades have these dams, and basically together with them determined how these dams should be deployed in the case of a very severe flood, so that they would know exactly when and where to put the dams to prevent or to protect the hospitals and nursing homes, rather than just the first house that's flooded. And the second thing, which is actually very cool, is that Switzerland has a training program for first responders that's coordinated on the federal level. And now this tool is included in this training program. So there's a training module for first responders where they can use this tool and learn or practice what they would do in such a case. And okay, and now that was on the first tool. I'll switch gears a bit, but stay with flooding.
I'll just ask a question.
Yes.
And excuse my ignorance here. I was just wondering, obviously I don't know how the infrastructure is set up in Switzerland, whether communication infrastructure or also energy infrastructure might be heavily impacted by flooding, and if so, whether you had considered incorporating that, because I know in Australia it's probably more with fires than flooding. I don't know, but I do remember there were reports where communication, especially for first responders and people who are calling for help,
Yes.
is a critical asset.
Yes, that's a very good question. So in terms of energy infrastructure, so the big energy infrastructure, so the nuclear power plants and the hydro dams, they are built in a way that they can withstand really extreme.
And are the transmission lines and everything underground?
Many transition, but then there are the power plants should be okay, but I mean there are regional distribution centers or even distribution centers in certain neighborhoods, and not all of them are really flood protected. And it happened in the past that yes, certain areas were without power. And
because that's, I suppose, you have that initial ramping up of impact, but then I suppose the effect of that impact over the longer term or the medium term is going to be influenced by those other types of infrastructure, and certainly communication. That initial
yes.
phase.
So at the moment, the emergency communication in Switzerland is still relying on AW, so radio. So every Swiss household is supposed to have a radio, still a working radio with batteries. So you can listen to the radio and you would get instructions on what to do via the radio. So that should be could be working even if your house is out of power, but it's in a transition phase now.
Interesting.
That was the traditional way of ensuring some resilience. And then of course the emergency services themselves, they have several communication networks that are independent of the public.
Yeah, but if the public, if they want to call for help.
Yes, there are limitations there. Yes. Thank you for this important question. I'll change to the second tool that I would like to introduce, which has the aim to provide some estimate of climate change impacts on floods in Switzerland. And there is we'll here risk sensitivity. Just a short summary of what do we know about floods and climate change in Switzerland. Of course, as all around the world, there's an increase in precipitation intensity with increasing temperatures. From this, we would expect that local scale floods and surface water floods would increase as well. The changes or the effects on floods in larger catchments are more uncertain because apologize, I deleted this one. There's also the influence of the soil moisture, whether the soils are very dry, sort of in a state of medium soil moisture, or whether they're saturated. There's a question of temperature. Basically, is most of the precipitation falling in liquid or in the solid phase? There's the question of snow melt. Some of the worst floods that Switzerland has experienced in recent years have been rain on snow events, where basically precipitation fell and then snow melted, and combined effect was huge. Basically, in summary, there's still some uncertainty, and for further information, I invite you to look at these Swiss hydrological scenarios. So we said, yeah, well, there is some need for further information. And basically, we looked at this question in two ways. First, taking a top-down approach, probably the more classical approach, starting from the climate affecting the weather, changing the precipitation, and would affect hydrology, and we would end up with some floods and damages. So what we did is we took the 9 scenarios and added a Clapeyron change to the precipitation, and then fed everything into the model train and looked at the effects on the impacts. And what you can see here is a summary. So each of these lines represents one of these 9 scenarios. The x-axis, you have the global warming levels. On the y-axis, you have the monetary damages. This is damages to buildings. And you can see with an increasing global warming level, you find an increase in the impacts. However, what is quite interesting when we then go and look into a bit more detail how this transition from change in precipitation to change in impacts looks like, we find that there is a nonlinear increase in the discharge and also in the damages. And this is summarized in this quite complex pattern here. So here you have, again, on the x-axis, the global warming levels, and then on the y-axis, the relative increase. The gray boxes, which are difficult to see, it's these boxes here. This is the precipitation change. So you can see it changes with this approximately 7% per degree warming level. I should say warming level was then translated again into local warming. So Switzerland warms a bit more than the global average. So it's Switzerland's 3 degrees is actually a bit warmer. But then what is interesting is if you compare the precipitation to the discharge, you can see that the discharge is increasing more than the precipitation. And if we compare the discharge to the building damages, which are the purple boxes, you can see that there is again a stronger increase. So I would like to take now a bit of time to explain why we see this nonlinear increase in the damages compared to the increases in precipitation. Maybe a quick note also on the discharge. I mean, this transfer from precipitation to discharge, of course, is strongly dependent on the hydrological model. There's some so this is just the results using this one particular hydrological model. But what we find is that this increase in discharge is really in this particular model related to a change in the runoff coefficient. It's just that the increasing intensity of the precipitation changes the hydrological response to a more Hortonian flow. So a lot more water just directly is translated into the rivers rather than into the soil. And there's also a bit of change in basically the snow hydrology. So there's more precipitation in liquid form relative to solid form. But it's really the damages that are interesting. And I would like to talk about this really strong increase in the damage and what is underlying the underlying effect. And to do this, I first need to introduce a second approach that we took, which is a more bottom-up approach, where we say, okay, let's first model a relationship between discharge and damages. Say we don't care how the discharge comes about, we are just interested for a specific discharge, how large are the damages? And this is illustrated here for one example catchment. And I would say that this is really one of the key figures of this presentation. So I'll walk you through it step by step. On the x-axis, you can see the discharge. On the y-axis, in this particular example, is the exposed population. And on the y-axis, on the right-hand side, it's the flooded area. And the red curve indicates the flooded area, the black curve, the exposed population. And what you can see is that this relationship between discharge and exposed population, flooded area, is nonlinear. So if you focus first at the population, you can see there's a strong increase in the number of affected people in this green area, not so much in terms of the flooded area. And then there is a strong increase again in these areas where the discharge is approximately 1,100 cubic meters per second. And this, basically the shape of this curve is really critical, because the shape of this curve tells you where sensitive areas are. If climate change is affecting peak discharge in this area here, we really don't care, because here there's protective infrastructure, and even if sort of the discharge changes from here to here, nothing happens. If climate change is, and I should mention this is the highest measured discharge for this particular catchment. If climate change is changing this flood events from here to here, we have a big problem, because this is really a large increase in the number of affected people. It's a bit less so in terms of the flooded areas. So there is this non-linearity between the impact and the discharge is really key. It's also key, it's not just key for climate risk assessment, but also for forecasting. If your forecasting uncertainty is right here, it's really a big problem, because there's a huge difference between this discharge at 650 or a discharge at 550. But if you're forecasting, if the forecasted uncertainty is somewhere here, basically it doesn't matter, because the impacts will be almost the same. So this, knowing this this curve can really help you with reframing forecast uncertainty and also reframing climate risk uncertainty. And this is what I'm going to show you how we did that. So we calculated these curves for all the different catchments in Switzerland, and then
on that previous figure, in range A and range B, are you highlighting those because of the non-linearities within them? In that range in a certain way?
Yeah, these two ranges are just examples of. So range A is a range where there's a big change in the.
So it's just you're highlighting those areas.
Yes, as two examples of yes, uncertainty here being really a challenge. Uncertainty in the gray range, yeah, not so much a challenge. Yeah. So we've analyzed all of these river sections in Switzerland, and then basically classified them according to how these risk curves, what the shape of these risk curves look like. And we basically classified the rivers into 3 categories, where sensitivity, and we defined the sensitivity basically as a combination of the first and the second derivative of these curves. So if there was a strong increase in the impacts, we would say, okay, this is a high risk or a high sensitivity area in this curve. And then we basically looked at whether the high sensitivity areas are in the lower tercile, in the middle tercile, or the upper tercile of this graph. And then we colored all the river sections according to whether they're in the lower tercile, these are the red rivers, in the middle tercile, or in the upper tercile. And this is basically an indication of where in Switzerland there's a high sensitivity of flood risk to climate change, would be the red areas, or whether it's a low sensitivity because the strong increase in the number of affected people or the number of affected buildings in this case is at the far end of the discharge distribution. So I'm going to show you a couple of examples. So this is one river section that's located here, that's red, the red category, and you can see, yes, the biggest increase in the number of affected buildings in this particular case is in the first tercile of the discharge, and hence it's labeled red. Here is an example of the yellow category. So this is a catchment where the biggest sensitivity is at very high discharge, and so a bit less concerning. And the final point that I would want to make here is that we did this for different types of exposure, buildings, people, workplaces, and you can see that the curves have different shapes. So the shape of this curve is sensitive to the exposure. And why do these curves have these shapes? Now I'm trying to explain that here very schematically. So we have this sensitivity, or this curve that indicates the damages as a function of the discharge, and you can see that there are 2 areas here where there's a strong increase in the damages. And if we have if you look at the upper schematic, this is a very schematic cross section through a river. So the river is in the middle, and then we have buildings to the left and the right of the river, and you can see a bit schematic topography. So if you imagine the flood levels rising, you can see there's basically a jump once the water reaches this first plateau. There's a huge increase in the number of affected buildings, and then it will remain stable because basically it needs to fill up the next this plateau. And then once the water reaches the second plateau, there's again a big jump. So the shape of this curve is specific to each river section, and it is a function of the topography and the spatial distribution of the exposure. And so this is what we need to consider. And then there's one last point that I want to make here is, as I said before, it's this geometry of the exposure that's really important. So here we have an example again of on the x-axis discharge, on the y-axis damages, and you can see that if here we have a flood, the highest ever registered flood in the current climate, and then if we say, okay, with climate change, the flood increases by 10%, there's some small increase in the damages because basically the water is slowly reaching more and more exposure. But then we can have some really critical situations, and these critical situations at least in Switzerland, are partially man-made. Because in Switzerland, as I mentioned before, we have this mandated flood protection, which is designed for a certain flood level, 1 in 100 or 1 in 300-year return period. And of course, I mean, Switzerland cannot build flood protection to some extremely high flood levels, because this is neither economic nor would it be nice in the in the landscape. It would just have concrete everywhere. So, but the problem is that in Switzerland there are building codes and there are spatial development codes, and if an area is protected by a dam, you're allowed to build buildings in this protected area. While you're not allowed to build buildings in an area that's that has a major flood risk in the current climate. However, with climate change, if floods exceed this protection level, you suddenly have a huge exposure, because people have been building houses right behind the dam because they thought it's safe. But it's only safe in the current climate and in the future climate. So this is why some of these extreme jumps in the number of affected buildings or in the damages are actually, as I said, man-made. It's actually then, once the protective infrastructure fails, all of a sudden you have a huge area that's affected. So this is something that we need to consider, where we need some actually legal changes and adaptation of these of the building code, the spatial planning, and also, I guess, communication of telling people, yes, your house is safe if the climate remains stationary, but changing climate, this might not be the case. So to summarize, there's a nonlinear relationship between precipitation increase, discharge, and damages. And one of the reasons for this nonlinear change is exactly what I'm highlighting here on the left-hand side. This damage sensitivity is floodplain specific, because it arises from this interaction of the geometry of the floodplain with the location of the exposure. And it's exposure specific, different for buildings and for roads or people. And the present day flood protection measures, the associated spatial planning, can contribute to those flood. With that, I thank you very much for your attention.
Fantastic. So questions, yes.
I think the input, this is very nice, illuminating presentation. My understanding is that the input to the system is precipitation
Yes.
and temperature.
Yes.
How high you can go in getting the inputs? So can you go to future, like 2070, 2100?
Yes. I mean, in principle, you could feed the output of a climate model into this chain, into this modeling chain. We have not done so because of the relatively poor resolution of the climate models in the past and the complex topography in Switzerland. So you need to do a lot of interpolation, which really increases the uncertainty. But now, with kilometer scale climate model outputs becoming available, yes, it would be possible to.
All right, okay, good. Thank you.
Really great the way that you had risk personnel and response people engaging with the first model. On the kind of second model, have you had interest from local government people or insurance companies or anybody like that to try and play around with it?
Yes, so, yes, from insurance companies. With local governments, so far, not so much, but yeah. So, but I mean, everything is online available in this tool. So if you're a local authority, you can look up your local river and see where the sensitivity lies.
Yeah.
So hopefully it will help in the prioritization of flood protection measures.
Or they could choose not to look at it
Yeah.
and then get sued later.
Yes, but hopefully it can help to choose where flood protection is most important in terms of sensitivity to climate change. Yeah.
And just one other question, just about, I guess, the validation process of the models, like how you went,
Yeah.
I don't think you talked about that very much, but just how you went about for both of the models, kind of testing them out.
So we have been comparing the results with data that we have from past floods. We know which areas were flooded. It's actually quite tricky to do the validation because in Switzerland, typically after a major flood event, something happens. So the new infrastructure is built.
Yeah, that's what I was wondering about, right?
So to compare, we actually have to remove this new built infrastructure to see whether, and we've done that for a couple, so they're basically the place where the person who's running the model, where he grew up and where he lives. So for this location, we have done all of this. But it's a lot of work, so we could not do that systematically across.
I imagine that's kind of the ongoing issue, right? That humans are always going to respond and change the environment. Yeah. So to the extent you can engage those councils or whoever it is and help train them up so they can do that work so you don't have to, that would be an amazing approach.
Yes.
It's really fascinating, and the distinction between the places that may be subject to these non-linearities versus not is striking. Can you say anything about the proportion of those sort of two cases? I guess what I'm asking is, to what extent is infrastructure that's been built on floodplains and therefore potentially exposed to these events in your graphic, where you've got your walls, but the 10% is going to be above those? Are you able to see from this sort of analysis where you can see where? So what infrastructure is at that?
Yes, I guess we could, yeah. We could do that.
But you haven't looked at it. Because I guess that would be a way of communicating the broader message, right? What does this mean at a national level for the amount of our infrastructure that is potentially, even though you thought you built it in the right place, that's what you were told, this is safe. It actually isn't. That could be quite a striking way to communicate the overall impact here.
I'm just thinking property prices.
Well,
Yes.
Yeah.
I mean, there are actually quite important political and economic.
That's right. There are significant political implications. I could imagine in Australia, if this sort of information were available. Well,
It is available.
it is available.
It hasn't been used the way this is.
Yeah.
Been used, yeah.
But there are examples where it's maybe been made available by less credible sources.
No,
And
Geoscience Australia kind of thing
and-
working on this.
yeah, But the less credible sources where that's become public, it's caused quite a media. And I could just imagine, yeah.
Yes, sort of this, as I said, in Switzerland, there are these flood, across Switzerland, all populated areas have been assessed for flood risk, and there are 3 different levels of flood risk zones, and there's one zone where you're not allowed to build or rebuild. And of course, once a property gets classified, falls into this category, it basically becomes worthless. And this has been a very painful political process to negotiate. There's a lot of negotiation of which areas fall into this zone and which. And this, of course, means that we have to think of a way of how to how to adapt this process and let people know that these zones are going to change over time.
So it means all the catchments of these rivers, Switzerland, are calibrated.
So this is for the river sections where we could obtain profiles, exact cross sections. So for most of the major rivers, we could obtain that, but all the small rivers are missing. So all the flash flood type floods are not included here.
Thanks. In the early stage of your flood model, you've got input information of precipitation and temperature. Is the purpose of the temperature data to determine what type of precipitation will fall? Or does it also factor in evaporation?
It's the evapotranspiration and the snow melt and whether precipitation is liquid or solid.
Yep. Okay. Is
Yeah.
wind important on that kind of scale at all?
Be honest, I don't know. And the reason is that we have relatively few good wind measurement stations in Switzerland, and wind is really varying very strongly and is really
very complex.
strongly influenced by local topography. So we just don't have a good data set to even estimate how big the wind influence could be.
And based on your intuition, would it make much of an improvement to the model if you had perfect wind input, or would it not be worth worrying about?
Locally, it can have a huge effect.
Yeah.
We know that it can locally enhance the affect snow melt quite substantially.
Right. Okay.
On the large on a larger catchment level, I would expect it to have more. I would expect that the uncertainties that we have from the spatial interpolation of the precipitation are larger than the wind.
Yeah. Right. Okay. Yeah. Thank you.
I have one last question about the scaling rate
Mhm.
that you use. So you assumed the Classius Clapeyron rate 7 degrees per Kelvin. In Australia, we've just gone through a process of trying to update our rainfall and runoff guidelines. And one of the outcomes of that was that shorter duration rainfall could be expected to increase at a higher rate. Is that true in Switzerland as well?
Yes.
Yeah. And so then I guess if you were going to take that into account, you'd have to look at the type of event.
Yes.
Yeah.
So here, these maybe I should go back. These 9 events that we were looking at, those are all multi-day events.
Yeah. Okay.
So they're so these are 3 to 5. Yeah. So it's either 3 days or 5 days.
Okay.
So these are really a cyclone sitting next to Switzerland and just bringing moist air towards the mountains.
Yeah.
Yeah.
Okay.
But once, also, we've completely, as I mentioned before, we've completely neglected the flash floods.
Yeah.
Because at the moment, we cannot model them in a good way because we don't have the observation.
Mm.
So these flash floods are mainly in catchments where we don't have discharge observations. So at the moment, we've just ignored them, but once we head towards the flash floods, it will be shorter precipitation durations, and then the super Clausius Clapeyron scaling becomes relevant. Yeah.
Any last questions before we break? Okay, well, I think we've got some food outside, so please join us to have some food and a drink and a chat to Olivia. But let's thank Olivia for her talk again.